So this segment, what we will talk about is, though we try to quantify the harmonics which will exist on a string of finite length, still there are some quantifications left out, means we can still quantify more very precisely. So that is what we are going to do in this segment, and that will again start from where? This equation, but I want to put these things back here. Okay, so I'll just I'll write it. What you do, see, what I'm going to do is this I'm putting back here, because this is what 2 pi f over c. K is omega over c, right? So this is omega over c. Last time we saw that it's that thing, and omega is 2 pi f over c. So here in place of f we will just put this, and here again it's nothing but 2 pi f. Here we will put this, and if you put that, you will get the equation which I am just going to write it. Y, x and t, it's an, I'll just tell why I'm putting this an, sine of pi n x over L cosine of pi n c over L times t minus phi n. Okay. Now this we are writing n because now everything has been quantized, right? The frequency has been quantized, so you can have only such frequencies, means possibility of such frequencies to be on the string, and that is why everywhere the phase also quantized, everything, the amplitude is quantized. So that is why we have now started putting a subscript n everywhere corresponding to which harmonic, first harmonic, second harmonic we are talking about. Yeah, so here for just completeness I can write here that f is nc over 2L, yeah, and which is nothing but n over 2L times t over rho. If you can replace c with this thing, okay. Now what we are set to do now is, for a moment you try to compare what you did with a finite string in a general way when you had two such thing, and the general expression of y x of t was half h x minus ct plus half h x plus ct minus 1 by c q x minus ct plus 1 over c q x plus ct, right. So this we discussed when we talked about also the finite string. Now what was that discussion? What is this discussion? Are they the same thing? Why did we do in two different segments? Means what is the relationship between them? Think for a moment. Okay.
So instead of a pulse, if you are sending sinusoids, then
Okay. When you said pulse, what exactly did you mean by pulse?
Maybe something like this, e power minus x.
Okay, some shape.
Yeah.
Okay. So that was related to, if I say, you are talking about this, right? Some function, okay, phi equal, some function like this and some function like this. So that's what you are talking about. Because you didn't solve for this, so you are not feeling it. I know. Because you wrote the code for this, so you are so confident about this. Yeah. So that's the benefit of writing a code and see these things happening. Okay. So this was the general solution of the wave equation with those two boundary conditions with these two initial conditions, right? And now we have come to this point. So the statement which I made now, out of that, how much has been covered and how much has not been? As I did, this is the general solution of the wave equation on a finite string with those boundary condition with these two initial conditions. Now here, what is missing? The initial conditions, because this is the general solution of the wave equation on a finite string with these two boundary conditions, but not with any initial conditions. We didn't talk about any initial condition till now. Did we talk anything? No. So think about that. If you are never right, so we just to come to this point, what have we done? We just use the property of what a rigid end does. That means it reflects at the same amplitude because it cannot eat away energy. That's the only thing which we used, nothing else. And the same thing on both sides, and from that analysis we came to this point. So we never said that there were some initial conditions. Okay. Though we now have a feeling that these are maybe some way related to the harmonics, means could be the modes, but still we don't know. Though we started our discussion with a hope that we will talk about the modes, but till now we are not, we haven't discussed anything about modes, right? We haven't. So now we are going towards that slowly to talk about the actual term mode in these conditions. Till now we said that these are the only possible waves of sinusoidal form which can exist. Okay. Now, so obviously the next step is to impose these initial conditions and to see how things will happen. Okay. So what would you do for that? So if I take this and yeah, so I'll write y x0 is nothing but y0 of x, right? And which will be equal to what? Okay, before that, I'll do one thing. I'll write another form of this which will be handy in doing that. Let me write in the other form. No, I'll write it here by removing it somewhat, or I'll take this. Arey, I mean, this is horrible. This always happens. Anyways, I'll not do that. So I'll take this down a bit. And I'll write it. What is happening? Okay. So I'll write now that thing. So an sine of again pi n x over L cosine of pi n c over L minus phi n, which is equal to thanks, which is equal to sine of, see here in this form you have two unknowns, right? Depending on the starting, you can have these things adjusted, and because now we are talking about starting conditions, so we have to now think about them. That's the reason why we are doing. And that two unknown information which we can set by initial things can be framed in another way. So that's what I am writing now. It's sorry. You can write this as pi n x over L times, I'll just write b n, this cos a minus b form you can just transfer into cos a cos b sin a sin b of pi n c over L t plus c n sine of pi n c over L t. Okay, we did nothing, just converted that form to this form, keeping the same number of unknowns. So the unknowns here are now b n's and c n's. Okay. Now we suppose think to write in this form. Now you just put t is equal to 0 in this expression. So this term just vanishes and you are left with, and then this one will be 1. So you have bn sine of pi n x over L. Okay. Now and you see that here when we wrote this, yeah, you write it, it's fine. See, this is, you have to visualize that every such n is a possibility, right? That means it's not that only one of those n is existing, and we are saying that any such n can be there. So that means all such n also can be there, because things are linear. Like the way we said that the forward moving wave and the leftward moving wave, they don't see each other, right? Because things are linear. The differential equation is linear, all are small deflections and all. So the same thing happens here. The n is equal to 1, the first harmonic, if it is there on the string, it doesn't mind if even n equal to 2 comes and stays there, because that thing is completely transparent to n equal to 1 case. So at a time all of them can exist on the same string, because they don't mind each other being there. So that is what you can represent as a sum over n, okay, of all these terms. So what we are now doing is this, its most general form, we wrote that this will be a sum of all the possibilities which are available to us, and that we took at time equal to 0, which will give us this, right? And what about the partial of y with t you take and evaluate this at 0? You take this thing, each, again every n, we are talking now in terms of the possibility of all n's, but then this, if you sum them up, is it not the v naught x? Because you took the partial with time, so you get the velocity profile, and then that you are looking at t equal to 0. So that will be, you will get something like summation of, if you take the differentiation, this will become a sine, so at t equal to 0 that will vanish, so this will remain, it will become a cos, and these terms will be there, but cos at t equal to 0 becomes 1, so Cn will come times sine, so sine pi n x over L, right, and all those things will be there, so n pi c over L, right, and again over all n. Okay, so does it tell anything now? Does it remind you of something? Yep, right. So they are nothing but the Fourier series representation of the velocity profile and the displacement profile, right? And then suppose now what does that tell you? Means physically, it is the mathematical representation of the whole thing, but what exactly do you mean when you say that this is the Fourier series representation? And then, okay, before we discuss this, I'll just write the expression which you get after you, if you want to evaluate them. So the Bn will be the 2 over L integration of y naught of x. You multiply sine pi mx over L, then you integrate it over the full length, and your Cn will be 2 over pi Cm integral from 0 to L v naught x on sine pi mx over L dx. So this is the normal Fourier series coefficients. Anything? Right? So that means given the y naughts and v naughts, you are able to calculate the coefficients. This integration can be evaluated, which you can substitute here to get the complete, so I'll write it there itself. So now y of xt is summation of all those, so sine n pi x over L times Bn. Achha, Bn was with cosine or sine? It was with Bn, we had with cosine. But okay, just a minute. But this is with, oh yeah, so then it's fine. This is that, then, oh sorry. This undo button and this one is always confusing. Times Bn cosine of, what was there? N pi c over L. N pi c over Lt plus Cn sine of N pi c over Lt over all n. So that means here you start with this and this given conditions, and then you calculate them by doing this, and then you replace here and you got the complete solution, right? Now what does this mean in English? If you want to explain this thing, because this is anyway the maths, in English if you want to explain this, what do you say? See, the thing is, why there? Here it's, whenever you have some shape of displacement, okay, now that has got what do I call? I'll draw another shape. Say y naught x is, say, like this. Now this shape can be broken into, because this is periodic again, so it can be broken into many sinusoids with their own amplitudes. So that is what is the Bn's, and which you had here. This is that sentence. Y naught x has got its own frequency components with different amplitudes. Okay, that means you are doing a Fourier series expansion of this. Means you are seeing the frequency components of this curve. Okay, that means this has now got some amplitudes for every frequency in a way, because see now the word frequency you should be very careful about, because this is x, so it is in terms of wave number sort of. Okay, so this is, but you are not wrong when you call it frequency when you are using a Fourier series, but it's yeah, you understand what I mean. So now these are those spatial frequencies, the amplitude of those spatial frequencies, and then this is the velocity profile spatial frequencies. Okay. Now with that you are giving weightages to different cosines and different sines. If you compare with the 1 degree of freedom system, the displacement was coming with cosine, velocity was coming with sine. So these are the things you see. Bn is coming from y naught x, Cn is coming from the v naught x, and they are defining your sine part and the cosine part. You remember that? Now sine part was the thing, because you have to start somewhere like this, and cosine things start with something like this. So this is the thing which is the displacement, and here to start from nothing, no displacement, you have to have some kinetic energy. So that is being provided by this, right? So these are the two components which is coming from the initial conditions of displacements and velocities, and again contributing towards that. So the other viewpoint what we had was, either you think in this way or else you say that there is a phase, because summation of a cosine and a sine is like a shifted cosine or a shifted sine, and the phase and the amplitude of that shifted cosine or sine are being dictated by the displacement and the velocity initial condition. How much potential energy you gave, how much kinetic energy you gave to start with. So that ratio will tell how much it will be shifted, or how much of this component and this component is there. Okay, and then whole of that thing acts as a coefficient to the shape's mode. These are the modes of the spatial thing, right? They are also signs only. Now they are getting weighted in a way with this thing, which has got also a phase and a sinusoidal.
So we are breaking the initial condition into sum of many harmonics in a way.
Yes. So, yep. So that means every initial condition has in it some harmonics, and then the shape decides which harmonic is in what proportion. This bn's, the number of bn's for different n, tells you how much of what frequency is there, and that will be dictated by what? The shape, right? So the shape of the initial condition of displacement of velocity tells you how much of kinetic energy type and how much of potential energy type initial conditions you are applying at what modes. The initial condition provides you the proportion of potential to kinetic energy at every mode, because as soon as you change these n's, these bn's and cn's change, right? Because they are attached to some n. So which means that suppose the fundamental, when n is equal to 1, how much energy was given as potential energy by this shape, because you might have given y naught and v naught x, right? And suppose v naught is something like this. You can start like this: velocity profile and displacement profile. Now each of them has their own, so they are, this function of space x. Now they can be seen in function of frequencies in a way. That means how do I say that if you consider this to be the period, this has got the different amount of bias toward different mode shapes, okay, to start with itself. So it is the starting thing. So there are two biases playing here, so that these are very important. The initial condition bias is like, to start with itself, how much of potential and how much of kinetic energy you are providing to whichever shape. Because when you split this thing, what you are doing? You are splitting it into many shapes, right? Like this. Like this. Now, when you split these amplitudes where the b ends, so that means this shape has some preference towards some of the shapes. and completely differently, means you change this, these Bn will completely change. So that tells the initial bias of displacement towards shapes. Similarly, this one, when you shift, again you will get something maybe like this, like here like this, and here like bad. What am I doing? So this is maybe like this, and this is like this. Okay, so this is the distribution of kinetic energy preference for this shape. So every shape of initial condition has its own internal preference towards a given shape.
But even the velocity is divided into the.
Obvious, because you see.
Here you are drawing the displacement contribution of the velocity, right? Means you were drawing. Earlier you were drawing on the right side. Now only the last.
Okay, this drawing here.
Yes, sir. On the right side, that is the displacement contribution from the velocity, right? Or is it?
No, I'm here. What I'm drawing is this again is say what should I say? Display. You are asking, are they the displacement components of the velocity?
No. I mean to say the velocity will effectively to be converted into a displacement, right?
So that will be done by. Okay, so that has been done when you integrated here by multiplying all these things. That has already been done. You differentiated it here, you know, and you came here. So this velocity, this has already been taken into account in this term. So that is why you see here there is a n here, whereas there is no n here, because the velocity's contribution depends on the frequency. That is why the component here is again is having a n, though these are the constants depending on the geometry, but with respect to frequency again there is a component here. So that's coming because you have already taken into the velocity aspect of it.
So velocity is also broken into half.
Yes. So that's why I'm emphasizing on the word that preference of distributing the kinetic energy. So this is the total kinetic energy. It represents the total kinetic energy of the system. This represents the total potential energy of the system. But then the system has its bias for different modes, how much potential it will give to which mode, how much kinetic it will give to which mode. And that preference has been told to us by Fourier that this is the preference that it will give. If you do the Fourier series analysis, you will know the preference of that type of velocity, that type of displacement. And now, so that is the first bias. Okay, so that is the first bias, how you start. Okay, that's the first thing. But then there is another bias of nature, that this whole thing now is a bias for every such mode in space now. See now, so this is a function of only space, this is a function of only time, right? Now think about the space function. It's a sign of particular. Now if you change n, you will go to higher and higher frequency distribution over space. Then that thing will oscillate at some frequency, but with what amplitude and what phase is given by these two things. Bn and Cn will give you two things, one is amplitude, one is phase. You can think always in that term, right? Now how much amplitude has come will be the amplitude for this shape, the bias shape, because okay, I'll write like this, your y this color is not good for. Now y x and t is a summation of, there is a sine function, I'll not sine, I'll write space function. These are all harmonic functions. Here it's a time function. Okay, but this time, so this is we have sine, and this is something like a cosine of something minus phi n. Right? So the previous thing, I just split them. So this is the space dependence, this is the time dependence. But you see here, now this whole thing is, you can think of this full thing as a coefficient to this function. Now what is that coefficient? Is it not the bias for this space dependence? These are again n, right? This space, everything n. N1, 2, 3, 4, everything is a different shape. And this one, if you see, this one is having unity amplitude, cos part, but this is the final amplitude. So now that means it will, how much it will increase or expand or contract this space thing. Over time is this cos part, because whatever the shape will come after multiplying this, that will be just oscillating between minus to plus, because this one is moving from -1 to +1 only. This part has two jobs. One is to oscillate this whole thing between -1 to +1 plus giving a phase, when to start type. But then this one is telling which shape, like suppose I do it here now. Now that is the first shape, this shape. Suppose for that an is a big one. So then this will be multiplied by a big number, if this is big for n equal to 1. And now suppose for n equal to 2, this is a very small number. Then this shape will be diminished by this, like that. And at the same time, and then it will start oscillating at the same frequency which corresponds to that, omega n of that. Okay, and this phase is telling that this is not exactly sine or cosine, it can be shifted a bit. And that's what is, this full thing is coming like a bias to the modes of space.
So effectively there are, the different modes are oscillating with certain frequency.
Obvious. So this is the last conclusion, that these are the space modes, which are obviously mode means they are different frequencies. They are oscillating at different frequencies, which is sitting here with that frequency. But what is its amplitude? That is decided by the liking of this initial condition for different modes, different frequencies, sort of. Modes
so whatever the initial condition, it is whatever solution that we are getting is effectively the oscillations of multiple modes.
Yep. Obvious. That's the meaning of everything. But the only problem is in summarizing that so I never do that, because what happens after a few years, you will remembering only that statement. All the things will be forgotten. That's the dangerous thing. Okay, so you should think that initial condition is doing some part of its part. it is distributing the kinetic energy and potential energy to different shapes. That's the first thing which is done at the beginning. Because at the beginning only, if some mode doesn't get any energy, then where is the question of it getting excited even? So that will depend on this shape, right? So that's what happens if you take this shape. Suppose you take y naught x to be one of the mode shape, then other modes are completely rejected. So that is where the bias comes. That shape has a bias towards only that. So it will not give any potential energy to anything. So there is no question of the final shape getting any of those modes. So that's the thing. And finally, yes, that's the thing which happens, that the final shape is a combination of all the modes. That's it. Now why we are calling them modes, time kya? Okay, time is they are independent of each other. What exactly do I mean by that? Because this is a very vague statement, right? Independent of each other. One is physically what it means is each of them can exist without affecting others. Okay. Like the ijk components of your thing, the normal vectors. So that is why the normal modes, the term, no, normal to each other. That is why no shadow of one on another, because they are perpendicular to each other. So light aayega to no shadow on others. So perpendicularity. Now here, what do you mean by normal? What is normal to what? If that context, if you see that modes are perpendicular to each other, right? That's what the normal word is coming from, the perpendicularity. Now what do you mean by here the modes are perpendicular to each other? The orthogonality is a more technical term. They say the modes are orthogonal to each other. So what it means is, you remember while deriving this, the Fourier series thing, you used the fact that sine n pi x over L times sine m pi x over L. If you integrate, it will be L over 2 if n is equal to m. If it is not, it is 0. Right? So that was the condition which was used to come at this point. Not condition, it's a fact. Now that fact is the definition of orthogonality of functions, of these two functions in that domain. If two functions you multiply and integrate over that domain, and whether it is 0 or 1, so based on that you call whether these functions are orthogonal to each other. So now whenever m is not equal to n, they are 0, and when m equal to n, it becomes L over 2. So that is why all these functions, so these modes, so these are modes right now, the shapes. Now each shape, when you multiply with another shape and integrate, it is 0. So that is the definition of orthogonality of functions. When they are 0, when you multiply and integrate over their domain, if it is 0, so that is the meaning or definition of orthogonality. And that is why the normal modes. So these are modes which are perpendicular to each other, and you use that fact to come to this point.